Greetings, mathematicians. In this video, we are going to be learning about the least common multiple and greatest common factor of monomials. But first, let's start with a quick warm-up. Go ahead and pause the video, give this problem a try, and then come back when you're ready to check your work. All right, now that you've had a chance to try this one, let's take a look. So first of all, they're asking us to come up with something close to the actual answer, which means they're asking us to estimate. So we're going to take all of these numerical values and we're going to round them off into nice round numbers to estimate with. So for day one, instead of 6,804 tickets, we're going to round that off and we're going to estimate it to be about 7,000 tickets. Day two, we'll round that to 4,000 tickets. Day three, we'll round that to 4,000 tickets. And instead of an exact price of $19 per ticket, we're going to estimate that at $20 per ticket. So if we take day one plus day two plus day three tickets, we're going to estimate that at 15,000 tickets sold times $20 each. That gives us our approximated answer of $300,000 total in ticket sales. Now moving on here, here's what's new. You've done least common multiple, LCM, and GCF, greatest common factor of numbers, in previous courses. But today we're going to review that a bit and then expand it to monomials, which means including variables. So first, some review here. So first, remember that a factor means that it's where we're breaking things down. So we did this in a previous lesson when we were working with square roots. And here, if we take 30, we could find the prime factorization, but that's just one way to factor 30. There are other ways too, so not every factorization is the prime factorization. So you could do 1 times 30, or you could do 2 times 15, or you could do 3 times 10, or you could do 5 times 6. When you list out every number that divides evenly into 30 in a list like this, that's called listing out all of the factors. Now, for now, we're just going to work with numbers, which is what you're familiar with, but shortly we'll be adding in some variables as well. Right, a little bit more vocabulary here. You might recall that some numbers are prime or composite. So for example, the number 5 is a prime number. That's kind of like where, when we were finding the prime factorization, that was a place where we stopped when we were making those factor trees. So that's a number that couldn't be broken down any further. What we meant by that was it was a number that had exactly 2 factors, 1 and itself. So 5 can only be written as 1 times 5. You can't break it down any further when you're working with whole numbers. But for example, 6 is not prime, because you could write it as 1 times 6, but you could also write it as 2 times 3. Now, just by convention, we're defining 1 as neither prime nor composite. So 1 only has 1 factor, just itself. And prime we're defining as having exactly 2 factors. So 1 is neither prime nor composite. So we'll do a couple examples here of looking at prime versus composite. So 41 you can write as 1 times 41. Not every number you can do that. So we could write 51 as 1 times 51. 121 we could write as 1 times 121. And then for moving on and trying to find other numbers, you might remember some tips and tricks from earlier. Like, for example, things that are divisible by 2, always end in an even number, like 2, 4, 6, 8, or 0. The trick for 3s, remember, that's where you add up the digits and see if that sum is divisible by 3. So in 41, 4 plus 1 is 5, and 5 is not divisible by 3. 51, 5 plus 1 is 6, and 6 is divisible by 3. So that tells me that 51 is divisible by 3. And then if I grab my calculator and I do 51 divided by 3, I'm going to get 17. 121, 2 plus 1 plus 1, that's 4. 4 is not divisible by 3, so 3 is not going to work there. Dividing by 4, that's another even number. Once you've ruled out 2, then nothing else even is going to work. 5, remember the rules for 5 is if the last digit is a 0 or a 5, it's divisible by 5. All of these have a last digit of 1. 6 is even. We've already ruled out all even numbers because this isn't divisible by 2, but the shortcut for 6 is if a number is divisible by both 2 and 3, then it's also divisible by 6. 7, there is a rule for 7, but it's not a great rule. It's just easier to grab your calculator and type the number in your calculator and do, for example, 41 divided by 7. See if you get a nice whole number. In this case, you don't. Same thing for 51, same thing for 121. You don't get nice numerical values there. 8 we've ruled out because we've ruled out all even numbers. The rule for 9s is similar to the rules for 3s. You add up the digits, and if the sum of the digits is divisible by 9, then your number is also divisible by 9. So we can check here, 4 plus 1 is 6, that is not divisible by 9. 5 plus 1 is 6, that's not divisible by 9. 1 plus 2 plus 1, that's 4, that's not divisible by 9. So none of these are going to be divisible by 9. 10, remember, those are things that end in zeros. None of these end in 0. 11 and forward, I don't really have nice rules for you. Again, it might be easier just to grab your calculator. And if you want to know where you can stop, what you can do is you can take the square root of each of these values, and that kind of gives you the middle point. Like the square root of 41 is approximately 6.4. And you need to check all of the numbers, so divide by 1, divide by 2, divide by 3, all the way up to 6. And we've actually already done that. We've divided it all the way up to 10. And that will tell you if you've checked all the possible values there. So it turns out 41 is prime because the only numbers that divide 41 are 1 and 41. Now moving on to 51, square root of 51, we've also checked all of these because we checked all the way up to 10 already, and square root of 51 was already 7. We really only needed to check things up to 7. And square root of 121, well, that one's actually 11. That one works out nicely. So 11 times 11 is 121. Now you don't write 11 twice when you have your list. You just write it once. And since these last two items have more than just two factors, one in itself, these two are composite. These next couple questions are review. I'm going to give you a little bit of time here to give these a try. Just a quick thing to help you remember here. Remember that prime factorization is when you make those factor trees like we did earlier in the year, where you're trying to simplify this as much as you can. So 8 can break down into 2 times 4, and 4 can break into 2 times 2. So you can rewrite 8 as 2 times 2 times 2, or 2 cubed. Either of those is an acceptable answer for the prime factorization of 8. And we'll do a couple more problems here, and you'll see here this last one is where we're going to start adding a bit of new information. So let's go with the 30. 30 we could write as 2 times 15, and 15 could be written as 3 times 5. So the prime factorization of 30 is 2 times 3 times 5. 24 could be written as 2 times 12. 12 could be written as 2 times 6. 6 could be written as 2 times 3. So the prime factorization of 24 is 2 times 2 times 2 times 3, or you could write that as 2 cubed times 3. Either one is good. 180 x squared y cubed. What you'll do for this is focus on the 180 first. So 180 could be 2 times 90. 90 would be 2 times 45. 45 would be 3 times 15, and 15 would be 3 times 5. And then the new part is the variables here at the end. So the x squared would be times x times x, and the y cubed would be times y times y times y. So you could leave it all expanded like that, or you could rewrite that as 2 squared times 3 squared times 5 times x squared times y cubed. Next up, you have a couple of practice problems here. So I'm going to have you pause the video and give these a try, and then come back to check your work. All right, now that you've tried those, here are the solutions for you to compare your answers to. And we will stop here for the moment before moving on to the next section. Bye for now.